In this video, let us look at testing mean mu when sigma is unknown. So you already know how to test mu if you have a large sample. So in that case, what we did basically ended up replacing sigma by s. Okay. So now in general, whether you have a large sample or a small sample, in general, this is the theory, how the theory goes. Whenever sigma is unknown, regardless of the sample size, we are trying to test mu. So this is kind of similar to that. We already looked at this one with confidence interval. So the same way pretty much. So the initial population, if you remember correct, with the confidence interval, this was one of the assumptions whenever you are, especially if you are dealing with a small n. So let us start with this way, okay? So especially this is a must-have assumption with a small n. So the initial, if you assume that the x has a normal distribution with mean, mu and sigma square, so in general sigma is unknown. So we want to test h naught, whether the mean is equal to this given mu naught value. So the all three possible alternative hypotheses: mu greater than mu naught, mu less than mu naught, and mu not equal to mu naught. So you take a random sample and the x bar will follow that. So under h naught, the x bar has so this value is going to be the mu naught. So everything is the same. So this is what we did before, all right? So this thing has a z curve. So you already know that with confidence interval, the minute we replace this thing by s, so this will turn into a t distribution. So of course, if n is very, very large, t is almost same as the z. So that's a different matter, okay? But this is correct whether n is small or large. So this will follow a t distribution. This is the one we will use to test this hypothesis against that. So our test statistic is this part, sample t, because we are going to compare against the t table value. Because of that, we say it's the sample t. So you calculate this thing using the sample values, so and compare against the t table value. Okay, so this thing has a degrees of freedom t distribution with degrees of freedom, sample size -1. So once you calculate that, say for example, if you want to check this one, if that is your alternative hypothesis, part A. So the rejection region is going to be on the upper tail. So this is the table value coming from the t table with the degrees of freedom n-1. So you need to pick that for given alpha level, the type 1 error. So you need to find the t table values such that the area to the right of that value is alpha. So that is coming from the t. So if this value, sample t, this one, is bigger than that cutoff, so this is the rejection region of the null hypothesis, then we reject the null and accept the alternative at that level. Okay, so that's the conclusion. So now the thing is that so the p-value, also we look at the p-value for the whenever the sigma is known, it's the same way. That concept is exactly the same. To figure out the p-value, what you do is that you set your cutoff right on the sample t value, this one. Sometimes this is known as the observed t also, means that there is a sample t coming out of your sample, okay? So you set up, this is exactly what we did to figure out the p-value. So you set it up, your cutoff right on there, and then use the t table, okay, with the degrees of freedom n-1, and the shaded area is going to be the p-value. So in the t table, you need to look at that degrees of freedom n-1, that row, okay, and then read as close as possible. and get this area. So that's the p-value. So part B is the same way. If this is the lower tail test, here is less than. So your rejection region, I did not write it down here. Rejection region is going to be to the left. So very much the same argument here. So part C, so not equal to, so there are two rejection regions. This part will stay the same, okay? The sample t or the observed t value. So then, you have two cutoffs, one to the left and one to the right. You split your alpha into two, alpha over 2 here and alpha over 2 here. But here the part is that this is the t distribution. Okay, so this is the t distribution with the degrees of freedom n minus 1. So then you get that cutoff from the t distribution, and if the sample t is going to be in here or in here, then you reject the null hypothesis and accept the alternative hypothesis at alpha level. Okay, so when it comes to the p-value, it's exactly the same. You set your cutoff on the t distribution, or set your cutoff right on that observed value, sample t value, this one. So once you set one cutoff, depend on whether it's a negative or positive, you have two cutoffs, so automatically there are two areas you need to look at the minute you set it. If it is here, that you set it right there. If it is on the other side, you set it on the other side. But the bottom line is that there are two shaded areas you need to look at. The p-value is going to be this area plus that area. Okay, so it's pretty much you need to get that one of the areas basically from the t-table with degrees of freedom n minus 1, and you need to multiply by 2. All right, so either that or it's depend on the t-table you are looking at. Some textbooks have that the t-table, the area in the middle. Okay, if that's the case, of course you don't have to multiply by 2, but so basically that p-value is this shaded area plus this shaded area. Okay, so you already know how to read the t-table anyway, so read your t-table. So the assumptions behind that, initial population must be a normal one. Right there is coming from that. It's the same assumptions you had with the confidence interval. Okay, it's going to be a normal one, and so that's very crucial if n is very small. But what happens is that if n is very large, of course the t-table value is getting closer and closer to the z-table value. So therefore that see, that's where the other method comes in. Actually, the other method, actually pretty much this is the right method all the time. So then the t-table value is almost same as the z-table value. By the way, if you are using a Minitab or any statistical software, so if you give the data, if you do not know the sigma, it's always using the t distribution. Okay, so it's always using the t, whether this n is large or whether this n is small. So always, once you give the data, it's always using the t. So in other words, this is the right way to do it. Okay, but for large n, so you have a choice if you want to, because they are almost the same. All right, so okay, so let us look at a couple of examples. So as far as the example is exactly the same now. Okay, so in this example, this is a water treatment facility. They wanted to keep the pH level around above 8.5, but according to this question it says that, so these are the data. They pull a random sample, and the random sample, the sample mean is 8.42, the pH level, the sample standard deviation is 0.16, the sample size is 17. So so here, does the sample provide sufficient evidence that the mean pH level in the water differs from 8.5? Okay, so it's asking whether it's differ from that. So we wanted to look at that. So in other words, so we want to check whether the mean is 8.5 or not. If you want to check whether it's more than 8.5 is greater. Okay, so but according to this you want to check whether it's differ from 8.5. So now the thing is that, so in here sigma is not given. All right, so sample size also 17. So regardless of that, this procedure is always correct whether you have a big sample or small sample. So especially now, this is a must. You have to use the t, okay, because the c is only going to be way off actually. So then x bar minus 8.5 is divided by square root of n. So the degrees of freedom 17 minus 1. So you calculate this one is going to be minus 2.05. So you need to come, the alpha is given, alpha is 0.1. So here it's a two-tailed test. So you need to split your alpha into 2, 0.1 divided by 2, 0.025. So from the t-table, find this value with the degrees of freedom 16. So that is going to be 1.746. It's coming from the t-table. So there's a 2 value minus and the plus. Okay. So this value is in both are, this is the critical region. In other words, the rejection region of the null. So this value is in here. So if this value is either in here or in here, you reject the null and accept the alternative. So you reject the null and accept the alternative at that level. In other words, it's differ from 8.5. That is your conclusion at that level. Sometimes this kind, the way you, instead of saying that reject H naught and accept that way, people say that test is significant at 0.1 level. So that's another way people talk the result. Okay, when you say significant, is that you reject the null, in other words. So the p-value, to figure out the p, is exactly the same. You set your cutoff right on that and then figure out this area. But the point is that now the degrees of freedom has to be 16. That's, you can read only that row from the t-table. You will get that area. Okay, this area plus this area is going to be 0.05. So part C, what assumptions is required for the hypothesis test of the part A to be valid? If you read this question, nowhere it says that this pH level follow a normal distribution. So you remember that small n. So that's a very crucial assumption. Okay. So in other words, for you to assure the validity of this procedure, so the initial distribution must be a normal one. In other words, this pH level has to follow a normal distribution. Okay, so that's that. So let us go to the other second example. So the second example is almost the same actually. So the second example, very quick, let me finish it. So this one, so your is the true mean amount of coffee filled in a jar so more than, actually this is more than 15.6 ounces. Okay, so you have that. So nothing is given other than you have 6 values. Okay, so basically you have to use the t. Of course, you have to also assume that the normal distribution, that is not given either. So once you do all the calculation, at the end, you need to say that the data should follow a normal distribution. Okay, so here, this one now, so the same way, 15.6, so the mean has to be more, figure out the mean and the standard deviation, and figure out the sample t is going to be that. And so here alpha is given 0.025, so but that is only one tail test. So let me stop here and start on the next video.